Hello and welcome to today's webinar with VoltDB and Full360 entitled How a Fast Real-Time Database Helps a $2 Billion Loyalty Program Launch Campaigns in Days Rather Than Months. My name is Peter Viscuso. I'll be the moderator for today's event. Before we begin, just a few housekeeping items. This is a live presentation through On24. You can't see that, but there are many other people on the call, so there's usually a slight delay, just a few seconds between slides. The presentation will last approximately 45 minutes, and we'll take questions after that. There'll be an archived version of the presentation available that we'll send to all registrants. You get an email from us with a link to the replay. The phone lines are muted to cut down on background noise, but we do welcome and encourage your questions. To submit a question, please type it into the chat tab on the On24 screen, and we'll attempt to answer as many questions as possible at the end. There are resources available in the resource window that you can check out during the presentation. Okay. So with that, let's kick it off. Let me introduce our speakers. First, we're going to hear from Ryan Betts, the CTO of VoltDB. Ryan was one of the initial developers of Volt's commercial product. He values his unique opportunity to work with customers, partners, and prospects. Last year, I think Ryan did over 200 separate customer events, so he's got really good understanding of customer perspective and problems. And then we'll hear from Rusty Ross, Solutions Architect at Full360. Rusty brings 2 decades of network sysadmin, DevOps, and software development experience to the Full360 team. He's an AWS certified architect, and he walks the blurry lines between all of these disciplines to architect and implement cloud infrastructure for Full360 clients worldwide. Also from Full360, we have Rohit Amarnath, who's founder and best title of the group, Chief Elastic Ninja at Full360. Rohit's a founder and a leading cloud computing and business of Full360, a leading cloud computing and business intelligence firm based in New York. In 2005, he heard about Vertica at its launch at an MIT conference. He caught wind of emerging technologies for cloud computing and DevOps. Soon after, he spearheaded adapting these technologies into providing a managed service for Vertica on the AWS cloud, and then was introduced to VoltDB and quickly adopted it into his client solutions. Okay, so that's it for introductions. Let me turn it over to Ryan Betts to kick off the presentation.
Thank you, Peter. I talk a lot about stacks, right? As we try to build big data or kind of data at scale applications, I really feel that there's a lot of education, really interesting conversation going on about how to solve those problems. And I'm really excited about today's webinar. Having seen a preview of this material, I think that the stack, the set of tools that Rusty and team has assembled to solve this loyalty problem is really quite interesting. So I'm going to just speak briefly about where VoltDB fits in this stack framework, and then we're going to hand it off to Rusty to talk through the use case. In a lot of organizations, there's a workflow or a life cycle that goes on around big data. An organization first starts to collect data. Once they've collected it, they find ways to make it interactive for analytics, for exploration, or data science. And as they find interesting insights or kind of prove out different hypotheses about customer segmentation or real-time utilization or seasonality or fraud patterns, they begin to produce analytic results or reports that they can use to make real-time judgments off of those insights. We kind of see this pattern. At first, you collect data, you explore it, you find some value in that exploration, you formalize that process in an analytics or reporting process, and then you need to act against the data that you've discovered in order to generate value. In order to accomplish this full cycle or this complete workflow, you really need more than one tool in many cases. So here's where the concept of a stack comes into play. What are some of the different tools that are commonly required to realize this full process? Well, we divide this into fast and big. And in the big corner, there are things that people are pretty familiar with, columnar OLAP warehouses, the Hadoop ecosystem, and the applications here are familiar to us. User segmentation, traditional BI and reporting, large data processing like building a massive search index, and data science like statistical clustering or understanding groupings of customers together. But in order to act in real time, you need a new set of technologies or a different set of technologies, and this is kind of the things that we put into the fast corner of the big data ring. And these fast technologies are tools that aren't so much concerned with very complex queries against large volumes of data, but rather they're often concerned with simpler but very high-frequency queries and transactions against high-velocity data feeds. So if you're familiar with big data as a combination of volume, velocity, and variety, and veracity, then you can consider that the fast corner is about velocity, the big corner is about volume. And in the fast corner, we're seeing a couple of different types of approaches. We're seeing streaming frameworks, we're seeing some in-memory OLAP, and then we also have products like VoltDB that propose that these fast data problems are really all about transactions. It's often about making real-time decisions against a combination of current context or session data or location data or user activity combined with the historical insights that you gained from the analytics that you ran on the big data side. So taking, for example, a user segmentation report, combining that with real-time user behavior on your platform and evaluating a set of campaign policies to decide if you should generate an offer to a user in real time. And that shows the full cycle of big and fast. It shows the ability to do analytics, to use those analytics in real time in a fast platform to improve a user experience. A lot of times we see people adopting technologies sort of in the order of this workflow, and actually I think Rohit not only has, I think, the best title of the group, but a biography that shows this perfectly, right? First, he started with tools like Vertica, right? Tools focused at the big data side of the problem. And as the industry has matured and as those analytics have matured, there's a growing business need to use that data in real time. Rohit has discovered tools like VoltDB to integrate into those solutions to provide real-time value. It's a great example of the transition combination of fast and big. Another way to phrase this is that there's a pretty basic problem out there. There's sensors, mobile, big SaaS applications, real-time customer-oriented applications that create streams of data that overwhelm legacy databases. They overwhelm them both in the volume of data created over time, necessitating new technology to store and analyze them historically, and they overwhelm legacy systems in terms of the velocity or the rate of new data that's created. But there are a lot of opportunities to monetize these real-time data feeds if only you could examine each event piecewise in context with its real-time session, real-time activity, and in combination with the historical analytics you've done. If you can do those things together, you could begin to write really interesting applications that are focused at personalization, fraud detection, customer experience, cross-offering, cross-selling. And at VoltDB, we think that that real-time component should be a transaction processing database, which must have the capabilities of storing data, running transactions, offering request-response-oriented applications, right, all in a high-speed transactional environment. If you put those pieces together, big and fast, you kind of see a traditional big data component. This is Hadoop or the Verticas of the world, in combination with a fast data component, together combined into a stack to solve that entire workflow, right? To collect, explore, analyze, and then finally act. I think we're going to see a great example of this a little less abstractly than I've put it here. I'm going to hand it off to Rusty at this point to talk through the loyalty program that they've built using VoltDB and some other technologies. So, Rusty?
Thank you so much, Ryan. So Ryan, what you call a use case, we like to call a success story. This is a production deployment that we've rolled out in the past month for a major loyalty program, one of the largest loyalty programs in the world for a major international airline. They've been incredibly happy with the success of this, as have we been. So I'm going to talk a little bit about the challenge we were faced with and some of the problems that were presented to us, and then we'll talk a little bit about how we met that challenge and how we actually rolled this out and what we did. So to talk about the challenge, who was this for? It was for, as I said, one of the largest loyalty programs in the world. They have 10 million members. Not only that, they have a need to deploy campaigns and develop them very, very quickly in a matter of weeks, not months. So the challenge was on us to deploy an infrastructure in which code development could be deployed nimbly and quickly. And that's one place we started in terms of designing this challenge. Also, not only are campaigns developed and deployed quickly, we also, as historically with this loyalty program, seen a very high open rate when email campaigns launch, something on the order of an 85% open rate. And not only an 85% open rate, but also a very fast open rate. We typically see very high traffic spikes almost immediately after new campaigns are launched. So that really dictated that we needed to really focus on making a highly scalable solution. And not only that, we're not serving static data here. These are complex web APIs serving complex web applications. There's a lot of CPU going on. There's a lot of data processing going on. And so we were going to really need to build a very robust architecture internally to be able to handle this. And because this loyalty program is so valuable to our client, and because it's been so successful, really service downtime just is not an option. So high availability was also of paramount importance when we took this challenge. So before I talk about how we did meet this challenge and did this, let me talk about how we did not do it. This is what I might call the old way of approaching this. What we did not do is we certainly did not deploy a monolithic web server, and we certainly did not deploy a monolithic code base on that web server, nor did we deploy a legacy database like MySQL or Postgres or even a NoSQL solution. We certainly did not deploy a database in a monolithic way. Why doesn't that work for us? Well, it should be pretty obvious based on the challenge points that I kind of raised at the top here. But let's just talk about it real quick. Obviously, if we've got a big monolithic web server with a monolithic code base, it's hard to scale. That really gives us two choices. We can either over-provision our server initially, trying to guess the maximum amount of traffic we might ever need to field with a solution like this. Or we can under-provision, and when we see traffic spikes down the road, we can cross our fingers and pray, neither of which is a very happy experience. Similarly, when we've got a monolithic server in production, it's very hard to update. It's hard to maintain. That should be pretty obvious. And then also it's hard to delegate development. So when we've got a single code base, it's hard to develop new chunks of a campaign that haven't been deployed yet, or to improve chunks that already exist in production that we might want to roll out a future version on. We'll talk a little bit more about that as we go along. Similarly, the downsides of sort of the old way of doing a database approach are pretty much similar to the downsides of an old school web approach, in which horizontal scaling is very, very difficult. Now, any of you folks out there that have used Postgres or MySQL know that it's possible to build clusters and read replicas, and there is some scaling possible. But to do that in a dynamic way is very, very difficult. And I'm sure anyone who out there who's worked with that can affirm that with me. It's also in the same way that a web server, a monolithic web server, is hard to maintain, so is a database server. It's hard to tune for performance. Again, both MySQL and Postgres can be tuned for performance, but that takes a lot of guesswork. And it's hard to do that in the midst of production when traffic needs can be very unpredictable. And finally, and maybe the most important in this particular application, is a legacy approach is slow because data resides on disk. We're typically disk bound by bottlenecking that comes from disk, which typically is going to be the largest bottleneck we see in any of our server infrastructure. So that was a big limitation for a loyalty program this large, and one in which we need transactions that are fast as we need them. So let's talk about the better way. How did we actually do this? Well, when considering how to design this, we started at the very bedrock, what we consider to be sort of the most important foundational piece of the whole contraption, and that is, of course, the database, this 10 million member database from which we start and derive our services. And so we didn't obviously have to look very far to choose VoltDB. And let's talk a little bit about kind of specifically why VoltDB was a great fit for this particular scenario. I'd say first and foremost, and I've put it at the top of our list, is because it's fast. Because the data resides in memory, we're not disk bound. And again, As Ryan mentioned, in some cases, fast data, it's all about velocity. In this case, velocity is of paramount importance. We're serving lots of small transactions to many, many members, and we just can't see any latency or downtime. It would not be tolerated. Well, VoltDB is performing like a charm. We're seeing hundreds of thousands of successful transactions per second. And beyond that, to move to my next point, unlike typical MySQL or Postgres installation, VoltDB is very easily horizontally scalable. So as our traffic needs increase over time, we can easily scale up the capacity of our VoltDB clusters and process even more transactions per second. Again, that's going to be of paramount importance as we move forward with this ever-growing project and deploy more and more campaigns. VoltDB is ACID compliant, which is very important in an application like this. VoltDB we found to be easy to set up and deploy within Docker. And I'd say hold that thought for a little bit. I'm going to get back to that because we approach Docker in some interesting ways. So I'll come back to that. And finally, VoltDB is a longtime partner of ours. We trust them. We've deployed VoltDB in a number of fast data situations, and it's served us well. So we really, as I said before, did not have to look far to choose VoltDB, but because in particular this deployment required special needs for high availability, scalability, ease and speed of migration, we feel that VoltDB was a particularly good fit for this loyalty program deployment. And we're so glad we chose it, and we're not looking back. So I mentioned a minute ago Docker, and we did containerize VoltDB into Docker. Now, I'm sure probably everyone out here on this call knows that Docker is a containerization platform which lets us pack applications and software deployments into isolated containers and deploy them across a fleet of hosts if we want. For those of you out there who have worked with Docker, I'll just throw in that we were able to develop a single Docker file to build these containers, which pulls VoltDB code from a repo, provisions everything we need within a Docker environment, builds a container, and allows us to instantiate a cluster of VoltDB containers in essentially a single CLI step. So we can get clusters up and running very, very quickly, very, very easily. And for instance, in this picture here, I show that we've got a 3-node VoltDB container cluster running in our environment. And one great thing that allows us to do is in the midst of production, because it is so easy to instantiate new clusters, we could spin up a parallel cluster in production while our first production cluster is running. If, for instance, we need to do a major schema migration or other migration related activities, we could spin up a parallel cluster and perhaps instantiating it from a snapshot. And when it's up and ready in production, phase out the original production cluster, thus doing a seamless migration where we have no downtime. We've done this right in the midst of production, and we've basically performed a fairly major database migration with no downtime. That would also be a great use case for a disaster recovery event. We can talk a little bit about that maybe in the Q&A period. So the other thing I mentioned is that VoltDB is incredibly horizontally scalable. And we find that to be even more the case in a Dockerized environment where, for instance, if we start with a 3-container cluster, but our capacity needs increase, it's very easy for us to add additional containers to that cluster to handle more capacity. So we're finding that Docker and VoltDB in this particular solution has been a fantastic fit. We're really glad we took that approach. So that's a little bit about how we approached the database scenario of this infrastructure, namely choosing VoltDB, and more than that, containerizing it within Docker. Let's talk a little bit about the web service aspect. Again, what we did not do was build a monolith. We did not work from a monolithic code base. Instead, what we did is we considered the concept of a fleet of web services. We broke that proverbial monolithic code base up into distinct services, which we like to call microservices, such as a points calculator or a status API or a goals campaign or campaigns yet to be launched that we will deliver, that will develop and deliver as future microservices. Working within the microservices model, there's some immediate advantages we found, some of them which are going to make me sound like a broken record, but I'm going to say them. The first advantage we found is that it allows individual microservices to be horizontally scalable. So for instance, if the goals campaign has unusually high traffic demands, we can horizontally scale that microservice independently of the other services without touching them, which is really, really great. Another benefit of working within the microservices model is the ease of software updates. Let's say, for instance, we want to roll out a version update to our status API microservice. Well, that's really great because we can delegate an isolated development team to build that new version or to update the current version. And when it's ready, they can spin instances of that new version into production right alongside the instances of the older version. And when we've got the newer versions up and running and available in production, we can retire the older versions, thus basically doing a live version update right in the midst of production with no downtime. And furthermore, in doing that, we haven't touched any of the other microservices. All of the microservices are decoupled from one another. It's really, really great. And sort of a final benefit in general with the microservices model is, I alluded to a minute ago, but it is the ability to delegate development talent. We can have an isolated development team work on the status API while we've got an entirely independent team building the next microservice of a campaign that's going to launch in 2 weeks. And that has great benefits in an infrastructure like this because, as I said before, we have very, very fast deployment demands from this client. And it's really important that we be able to develop and deploy as quickly and as nimbly as possible. And we found that the microservices model has really, really facilitated that, and it's also made the client very, very happy. So as you maybe can imagine, we didn't just stop at working in a microservices model. We took the next step, and we actually containerized those microservices so that each microservice is a distinct Docker image that can be instantiated as a Docker container. So for instance, we could have 3 Docker containers running the cross-promo campaign microservice. Well, we've got 4 containers serving up the points calculator microservice. And as I've alluded to before, that presents all sorts of benefits in terms of horizontal scalability, high availability, and again, ease and speed of deployment. Those benefits that we get from Docker, though, do prevent one challenge. And let's talk about that. And that challenge is discovery. So what do I mean by that? Well, what I mean by that is this. Let's look at this example. So in our environment in which we've basically containerized all of our production resources that we serve up, they're somewhat ephemeral in nature, and here's why. In this picture, as you can see, we've got, let's say, 4 Docker containers serving up the VoltDB service as part of a cluster. Let's say we have 5 instances of Docker containers providing the member API service, 3 Docker containers providing the calculator microservice, and so on and so on. But an hour from now, if we have a traffic spike, we might scale up some of those resources, and there might be additional containers that weren't here right now. Similarly, we could have a container fail. We could have a container disappear due to a scaled down event if traffic needs deplete over time. So because of the ephemerality of these resources, it's really important that the resources we have that need to access these services know where to find them, particularly our front-end load balancers that direct traffic inbound. And frankly, microservices themselves, some of which have codependencies on other microservices, and they need a way to be able to find their sibling services within our environment. So the way we solve the discovery problem is by using Consul, which I'm sure many of you on this call know is a terrific service discovery mechanism. It's open source, and it's written by the folks at HashiCorp. And for those of you who have not worked with Consul, generally the way it works is this. In this example here that we've got up on the screen, when we instantiate a container, for instance, let's say this VoltDB container just to the right of the Consul logo, it comes into the world and it announces to Consul, hey, I've been born, here I am in this environment, and I provide the VoltDB service, and Consul takes note of that. When we spin up a member API container, that member API container talks to Consul, says, hey, here I am, I'm a member API container. Now you know that I provide this service. If you need me, here I am. Consul, on the other hand, provides a DNS interface for resources that need these services to be able to find them in an abstracted way, so that a resource like a front-end load balancer or a microservice that depends on another microservice can do a DNS lookup on an abstracted DNS endpoint, such as voltdb.service.console, and be assured that when it makes that query, it will receive back the location of a single healthy instance of a container that provides the service that it is looking for. Now, notice I said healthy service, and that's really, really important in our infrastructure. So as these containers register with Consul, Console institutes a health check on those registrations. And in our environment, we actually perform that health check every 10 seconds on every registered resource, so that if a container fails or disappears due to a scale-down event, Console will know that the health check has failed almost instantly and will not try to direct traffic to that container. So Console's been working great for us in this way, and it solves the discovery problem, which is really one of the challenges that's presented by using Docker and by provisioning this infrastructure in an ephemeral way. So let's just take a moment to just talk about the kind of the major elements that I've covered so far. We obviously started at the bedrock of this whole solution, which we consider to be the database, and that's VoltDB, and it's working fantastically. Beyond that, I talked about Docker, and as I mentioned, we've containerized all of our production resources, and that provides all sorts of benefits in the name of scalability, high availability, quick and easy deployments. But those advantages, as I said, present a discovery challenge, which we solve in what we think is a pretty darn elegant way using Console. And then, of course, we build all of this infrastructure in the cloud in AWS. Now, as everybody on this call knows, AWS provides myriad services and resources, many of which we leverage in this particular infrastructure, but one of which is particularly apropos to what I'm talking about, and that's auto-scaling. So I'll talk a little bit about it as we move forward, but essentially we leverage auto-scaling in this solution to do all of the horizontal scaling that I won't shut up about in an automated way so that we do not have to manually monitor traffic needs over time and initiate those scaling events ourselves, and it's working really, really, really well. So that said, let's take a look at the big picture in the context of AWS within the cloud. So the shot that I've got up on the screen now hopefully kind of demonstrates in a graphic way what this infrastructure looks like in totality within the AWS environment. So let's just talk through it really quickly. If you look at the top of this picture, you'll see this brown box labeled AWS Elastic Load Balancer, and that's the front-end endpoint for all of our infrastructure. Any of external requests that are coming in from the outside world to reach our services will hit that load balancer, and the load balancer will direct those requests inbound to our internal infrastructure. So what does our internal infrastructure look like? Well, it should be starting to come clear based on what we've been talking about, but let's look at it a little more specifically. If you look at these 4 quadrants I have below the load balancer, let's start on the top left. I've labeled that proxies, and that's an auto-scaling group of a type of node that we simply call a proxy node. Now, what is a proxy node? It's actually a custom node that we've designed that does a very, very simple job, and that job is this, is that it accepts an inbound request that's sent to it from the load balancer, which in its right is sent from the outside world. That request comes into the proxy node, and the proxy node looks at the request and determines which specific microservice the requester is trying to reach. So upon doing that, it knows that its job is then to direct that request to a container, a healthy container, that provides the microservice that's being requested at that time. We'll talk a little bit more about the details about that in a second. In the top right quadrant is another auto-scaling group of simply of generic Docker hosts, which are hosting the Docker containers that serve up all of the microservices that I've been talking about throughout this chat. Down in the bottom left is a cluster of console nodes, which provides the discovery services we've been talking about. And of course, in the bottom right is another fleet of Docker hosts which are hosting Docker containers of VoltDB in a cluster, which provide the database foundation of this entire solution. Okay, so let's talk a little bit, or maybe just kind of review a little bit exactly how registration works in terms of the discovery component in this environment. So as I said, as these containers come up, they register with Console. In this picture, you can see that each of these VoltDB containers tells Console that it's a container that provides the VoltDB service and that it's healthy. Console begins to do a health check on those containers and keeps track of them over time. Secondarily, in a very similar way, all of our microservice containers do the same thing. Each of them advertises to Console the specific microservice that it provides. And as Console learns about those registrations, it health checks them and knows that it can direct traffic to them when it gets DNS requests from resources that are trying to reach those microservices. And then finally, there's one more registration component, And that's the proxy nodes themselves. And those proxy nodes don't register to console, but rather they register to the AWS Elastic Load Balancer so that the load balancer knows where it can direct requests that come in from the outside world. So now let's talk about what does it look like when a request comes in from the outside world. In this example here, let's say we've got actually a real human in a browser in the outside world, somewhere strewn halfway across the world, trying to reach our public DNS endpoint, and specifically, as you can see in this URL, trying to reach a specific microservice of ours, in particular in this example, the member API microservice. So as that request comes in, as I mentioned, the public endpoint for all our infrastructure is the load balancer. That request hits the load balancer in AWS. Now, the load balancer already knows about our proxy nodes because they have registered with the load balancer. So the load balancer directs that request inbound to an instance, a healthy instance of a proxy node. Doesn't matter which one, they're all stateless, but the load balancer knows that we have a fleet of them, and it finds a healthy one and directs that request inbound. Now, the proxy node, which receives that request, looks at the URL and says, okay, I see the requester is looking to access the member API microservice. So I obviously need to figure out where to find a healthy container providing the member API microservice. So it performs a DNS query off of console, which gives it the location of a healthy container. And in this example, we'll say it's the little red containers that I've drawn in the top right quadrant of this picture. So once the proxy node knows where a healthy instance of a container providing the member API microservice is, it directs that request inbound, and that container can actually answer the request because it actually serves up the member API microservice. Now, the member API microservice in this particular scenario is special in that it needs to make a request of its own. It actually needs to access the member database that's being served by VoltDB to query that database so that it can serve an answer back to the external requester. So the member API container itself does a DNS query very much like the one the proxy node does. It asks console for the location of a healthy instance of a container providing the VoltDB service. Again, doesn't matter which one, it just needs a healthy one. So when it gets its answer from console, it knows where to send that request. It makes the database request. It gets a very fast transactional answer because we're using VoltDB. And the transaction on the inbound is complete, and the member API microservice can answer back upstream as you trace the arrows backwards back to the initial requester, and the initial requester gets a response. So that's sort of the chain of command in terms of how requests are routed and how they come in and out of our infrastructure in a somewhat ephemeral way. Now, as it's probably clear, this infrastructure is really helpful to meet the needs of scaling. I've been talking about that all the way through. So let's talk about that a little bit. Let's say we get traffic spikes coming in to our Elastic Load Balancer, maybe even unexpected ones. Well, that's no problem, because as you can see, we have a couple scaling vectors here. In our proxy autoscaling group on the top left and our microservices Docker host autoscaling group on the top right, those are independent scaling vectors. If our proxy nodes suddenly become or about to become overwhelmed, the autoscaling group will kick in and instantiate more instances of proxy nodes to balance out the traffic better. And similarly, independently, the same thing can happen in the Docker host autoscaling group. If our Docker containers start to become overwhelmed, that autoscaling group will kick in and instantiate more Docker hosts to host more microservice containers. And therefore, we're able to handle more traffic. Similarly, if traffic needs go down, the autoscaling group will kick in and diminish those resources so that we're not paying for resources that we don't need. Yes. So let's also talk about how this infrastructure is resilient to failure, because also high availability was a big challenge of this project. So it should be clear, but let's just look at it. Because these essential resources are in autoscaling groups, let's say, for instance, that we lose a Docker host containing some of our microservice containers that's in production. Let's say this Docker host on the left fails and disappears. Well, that's no problem, because as soon as that node disappears, console will know that the containers living on that node are no longer healthy and will not try to direct traffic inbound to containers that don't exist. Beyond that, the autoscaling group will realize pretty quickly that it's below capacity, that it doesn't have enough nodes to meet the capacity that it needs to meet, and it will spin up a replacement node pretty darn quickly. But it actually doesn't matter exactly how long that takes, because we still see no downtime time. We will never be directing requests to a container that's failed or disappeared. We will always be directing requests to a healthy container that exists in our infrastructure. And so I think that traces through kind of how we kind of meet the needs in this infrastructure. Why don't we turn it over to questions, and we'll see what comes up from there and elaborate as necessary.
Yep, thanks, Rusty. This is Peter, and as we said before, if you have a question, type it into the chat window. I'm actually going to turn it over to Ryan. Ryan had a question.
Yeah, I think that's really cool. And I've been pitching a lot of microservices content here internally in VoltDB, and it's really fun to see a production use case that's using those concepts. One thing I was curious about as you were talking through this is, is there caching of those console responses to the Volt servers, or what do you see as the total latency through this stack when as these different lookups and proxy hops need to be made?
If you may want to elaborate your question if I answered the wrong question, but what I think you're asking is latency between queries to consoles or registrations that go to console?
Yeah, I was just curious about how frequently console is pinged. Is it per request or?
No, so basically the registration, we run console in a cluster, and to actually elaborate a little bit, I've simplified the console deployment a little bit for illustrative purposes, but we actually run a console agent on every one of the EC2 hosts that we put into AWS. So the registrations, when a container, for instance, a VoltDB container comes up on a Docker host, that registration actually goes to a local console agent on the host itself. And due to the gossip protocol that's implemented in console, and that could probably be a whole talk we could do in the future on its own. But due to the gossip protocol, the registration that goes to the local agent on that host spreads very, very quickly. Now, the console cluster that I've depicted in that diagram is actually a cluster of servers. So those are the authoritative source of truth. But in general, we see very, very low latency for those registrations. And then, as I mentioned, in regards to the health checks, that's a configurable property. We're doing 10-second health checks because we find that since we've got services kind of over-covered and over-provisioned a little bit anyway, we can tolerate sort of 10 seconds of possible failure before a failed node is discovered. But that is something that could be tuned. And if for some reason we were finding that we were getting numerous failed requests due to the 10-second period when a node had failed, but its health check had not yet failed, that's something we could dial down quite a bit. But we're trying to keep the overhead on that a little bit low, and we're currently doing that at 10 seconds.
Great, Rusty, thanks. We had a question from the audience. It says, can you explain the responsibility split between the Elastic Load Balancer and the proxies in a little more detail?
Absolutely, yeah, and it's certainly a sensible question as to, well, why the heck didn't you just use an ELB and have that direct traffic inbound? There's a couple reasons we did that. One is that we wanted some control over the proxy nodes themselves. We wanted those to be able to auto-scale independently of the ELB, and more so than that, we really wanted to be able to control over how we sub-routed traffic to specific microservices now and in the future. So we wanted that sort of intermediate step where we got a chance to take a look at the URL and say, okay, based on this URL, we're going to direct this request inbound to a specific container service. And there might be ways to implement that on a bare ELB, but certainly not with the granularity that we were looking to do it, and certainly not without the control that we were looking to do it. I might just jump in, and this is slightly off topic, but I do want to, it's somewhat on this vein. I just want to mention, so as part of that, those custom proxy groups that we're auto-scaling, and the second scaling vector, basically the Docker host that hosts the microservice containers. Those are basically two independent scaling vectors that can scale entirely separately of one another. And I just want to mention, we actually envision in the near future a third independent scaling vector in which we would scale in a very granular way the provisioning of the microservice containers within the host themselves. And we plan to do that using a new AWS service, which many people have heard of, called ECS, or Elastic Container Service, which is currently in beta. So we actually envision that we are going to roll that into this infrastructure as well, and ultimately wind up with essentially three independent scaling vectors to handle capacity ups and downs in terms of the life of this project.
Great, thanks. Yeah, Ryan.
So Rusty, how do you do logging and tracing through these different components?
Say that again?
I'm curious, if you've given some thought to how you do logging or request tracing, kind of monitoring of some of these different components.
Absolutely. And I would say that's sort of two different topics. In terms of logging the services themselves, we have and are actually developing new techniques to basically stream logs from a fleet of containers all providing the same service to a single point of logging in S3, probably using a Fluent D process. On the flip side, and what I think you may have been more specifically asking is how do we log maybe node failures and service registrations? If that's not your question, I'm sorry. That's the one I'll answer. The way we do that is Consul, I've, again, sort of greatly simplified some of the feature set of Consul, but Consul provides the ability to post watches on service registration changes and do all sorts of monitoring at the Consul cluster level. So there are ways that we can integrate the Consul API to determine when we've got health checks failing and when we have new nodes scaling up and registering with Consul. So we do a fair amount of monitoring via the Consul API on that front.
This is Rohit here. Just to add to Rusty's answer, we also collect container statistics and we stream it using a tool called Prometheus for visualization of that time series data.
And we're able to present that. We're also able, just to pitch in on that, we're able to present Prometheus graphs in some very kind of visually rich ways, which not only are helpful to us as sort of in terms of managing this infrastructure, but they're also helpful in terms of presenting this back to the business itself. We've been able to present some visuals, which have been very pleasing for folks on the agency side to take a look and to kind of see how usage is going. So those kind of what I would call sort of semi-public metrics have also been pretty helpful.
Great. Thank you, Rusty. And that looks like it for questions. Before we wrap up, if I could take the opportunity, VoltDB's founder, Mike Stonebreaker, had a very big day today. He was announced as the 2014 winner of the ACM Turing Award. It's the most prestigious award in computer science. We want to say congratulations to Mike and wish him the best. So we're very happy and proud about that. As I said earlier, everybody that registered, thanks, will get a follow-up from us with a link to the webinar and the slides. We thank you for attending. Thanks so much to Rusty and Rohit for their contribution. Some of the coolest material I've seen in a while, and it's terrific. All right, that's it. Thanks.
Thanks so much for having us. We're so happy to be here today. Thank you.
Thank you.